Hi, Mr. King again. This is part 2 of our Law of Cosines lesson. And I'm going to begin here with Heron's formula, which allows us to find the area of a triangle if we know all three side lengths. We're not going to derive this formula, but we're going to just use it. So it says the area of a triangle, and this is not necessarily a right triangle, is the square root of s times s minus a times s minus b times s minus c, where s is defined as the half perimeter of the triangle. So it's 1/2 the sum of a plus b plus c. This is very easy to use. So in this example, we're given a triangle where we know the three sides. We do not know any of the angles. We do not need to know any of the angles. We'll round our answer to the nearest tenth here. So the first thing we need is the half perimeter. And it's equal to 1/2 the sum of 11 plus 20 plus 13. That's 21 and 13, which is 34, and half of 44 is 22. So we've got s. So the area is going to be the square root of 22 times 22 minus 11 times 22 minus 20 times 22 minus 13. This will give us the square root of 22 times 11 times 2 times 9. And this ends up giving us the square root of 4,356, which happens to be a perfect square. And this is 66. And that's the area of our triangle. In the next example, we're going to use another formula for finding the area of a triangle. And this time we know two side lengths and one angle, and we want to find the area. There are three versions of this. So area could be 1/2 BC times sine of A, or 1/2 AC times sine of B, or 1/2 AB times sine of C. And as before with Law of Cosines in this lesson, part 1 of the lesson, we saw that there was a nice pattern, and if we knew one of the forms, say we knew this form here, we could figure out the others. Now, one thing that stays the same here is that it's always the area of the triangle. But if we use AC, we need sine of B. If we use AB, we need sine of C, and so on. So again, this is pretty straightforward to use. Now this time, we know three sides and one angle. And this allows us to find the area of this triangle. Which one should we use? We know three sides, so that means we could use any of these formulas that involve the side lengths. But we got to pay attention to which angle we know. It's angle C that we know, isn't it? So that means we're going to use 1/2 AB sine of C. So this is 1/2. A is over here, it's 11.3. B is over here, it's 27.5. And then we're going to multiply by the sine of 117 degrees. And this calculation leads to the following for the area. It's approximately 138. Let's look at an application problem involving the law of cosines. Now, not all of this is too visible, so let me just add a little detail here. Each side of this double-sided crane is 10 feet in length. And there's an angle here in the middle. That angle is 128 degrees. So if we were just to draw a quick sketch, and we can see with the pink hypotenuse here, that's opposite the 128 degrees. So we have a triangle that looks something like this. We don't know this length, and we're supposed to find that length that goes between points A and B. This is 128 degrees, 10 feet, 10 feet. Clearly, this is a side angle side situation. And I'm just going to label this length B. This must be angle B then. And we can apply the law of sines here. We will assume two significant figures. So if we want little b squared, that length, it's going to be a squared plus b squared minus 2ab cosine of angle B. That's the form. And the numbers look like this. A and B are both 10s, so 10 squared plus 10 squared minus 2 times 10 times 10 times the cosine of that 128 degrees. This leads to 200 minus 200 times the cosine of 128 degrees. And this brings us to about 323.132. And when we take the square root of both sides, we arrive at approximately 18 feet, which is our answer. Which seems reasonable if these side lengths here are each 10 and we've got this angle between them. In this next problem, similar but different. There's a weight supported by two cables. Here's our weight. And the angles of the cables are different. They're both question marked here. We know this length of cable is 45 feet. This length is 60 feet. And we know the distance from here to here is at 90 feet. We're asked to find what the angles are, where the question marks are, the angles from the beam to each cable. And so there are two of those angles. Let's call this angle over here A, and let's call this one B. That would make this angle, this one C. That would make this one B over here. And clearly this would be side length B, side length C, side length A. And we can work from a formula for angle A that we've seen before. And it's that the arc cosine of B squared plus C squared minus A squared divided by 2BC. That's angle A. And if we plug in our numbers, let's see what we have. We have the arc cosine. B squared is 90 squared, plus C squared, which is 45 squared, minus 60 squared. 60 is, of course, what A is, divided by 2 times 90 times 45. And dot, dot, dot. You can go through the math, use your calculator, and we wind up at 36.336 degrees, which is approximately 36 degrees if we assume two significant figures. Now we're still looking for one more angle, and we can use the law of sines again. In that first example, of course, we used side angle side. And will we be doing side angle side again? Yes, we will, because we'll be looking at going from this 90 feet length to this 60 feet length, and then the angle we're looking for is this angle C in here. And when we go through this process, we'll see that C is equal to the arc cosine of 90 squared plus 60 squared minus 45 squared. All the numbers are the same, they're rearranged. And this is over 2 times 90 times 60. And when we crunch through this, we get to 26.3843 degrees, which is approximately 26 degrees. And now we have our angles, and those angles should add up to 180. Well, of course we don't know the last angle, but we could find it easily, couldn't we? And that concludes our lesson. But wait a moment, there's one thing I forgot. I promised in part 1 that I would leave a page in the notes that showed you how the law of cosines was derived. And I'm going to scroll this page slowly. It's all done, and you can study it by freezing the frame in the video. And you can study this if you're curious about how the law of cosines was derived. It all began with an oblique triangle. The dotted line is a height. It's brought down. It's a perpendicular bisector to the x-axis here. And I believe this proof involves some identities. It involves figuring out some trig values at one point, maybe. Well, maybe that was just to figure out something. I forget what. Anyway, I'm meandering here. So something important here is that x is equal to c cosine of theta in this problem. X, y, and c are the lengths. C is the hypotenuse. And by the way, that's for this little triangle that's on the side here. That guy. And where did the rest of this proof go? Was that it? I think I just blew that part. I think there's a page missing. I gotta go get it. Hold on. Okay, so I found the missing page. I forgot to move it up. And here it is. So a little bit more work here. As we can see in this case, we've moved on from using the triangle we created that was a right triangle back to the original oblique triangle here. Point on, we're going to do some substitutions. Up here we can see that x is c cosine of b and y is c sine of b. And we can see that x occurs here in our formula for b and y occurs here. So we're going to do a substitution. And we'll get the following, that this is the square root of a minus c cosine of b, that's squared, plus c sine of b minus 0 squared, like so. And that's basically the formula for the distance between A and C, these two vertices, using the distance formula in the xy plane. This can be expanded, so we'll get a squared minus 2ac cosine of b. Interesting, that looks familiar. C squared cosine squared b plus c squared sine squared b. And this is all under the radical. This can be rearranged a little bit. We'll get a squared minus 2ac cosine of b plus c squared sine squared b plus cosine squared b, which is the Pythagorean trig identity right here. That's equal to 1. So now we get to the point where we have this equal to a squared minus 2ac cosine of b plus c squared. This was equal to b, and if we square both sides, of course this goes to 1, we wind up with a squared minus 2ac cosine of b plus c squared. And if we rearrange this, a squared, b squared is a squared plus c squared minus 2ac cosine of b. And there is one of the versions of the law of cosines. And of course, the other versions can be gotten from this version by similar arguments. Again, to understand this fully, you need to go back and carefully go through the steps in this derivation, because I did not explain everything. And that's our lesson. Thank you.